Okay, so good evening, everyone. So it's 4:05, so let's get started. Welcome to Comp 5801H 4900A, Generative AI and Large Language Models. I will be your instructor for the course. I am Sriram Subramanian. I'm an assistant professor and Canada Research Chair here at Carleton. I'm also affiliated with the Vector Institute for Artificial Intelligence in Toronto and the Squash-Friesman Institute for Technology and Society in Toronto. Okay. So there is a range of research topics that I work on, but my core area of research is in artificial intelligence and machine learning. And the majority of my research is in reinforcement learning, where I work on several subfields of reinforcement learning, multi-agent reinforcement learning, distributional reinforcement learning, offline reinforcement learning, and so on. And another major aspect of my research is in generative artificial intelligence. And I work on foundation models, transformers, diffusion models, attention mechanisms, as well as AI safety. This is a good complement to this course because this course is also on generative AI and it is a core part of my research. There are other areas that I work on as well, like game theory and AI applications. So almost all of this course will be on generative AI. I will touch upon reinforcement learning in the middle, but the core aspect of the course will be on generative artificial intelligence. But if you're interested in my other research areas, you're always welcome to come and speak to me. And I mean, you're always welcome to discuss those other aspects with me. I collaborate widely with the industry as well as academia all across Canada and all across the globe. Some of my collaborations are listed here. Right. So for today, we are going to just introduce the course. We are going to give I'm just going to give an overview of the course, so you can just feel relaxed. There's going to be no hard concepts being introduced today, so you can relax. Just take it easy. I'll give an overview of what I'm going to talk about during the rest of the lectures. I will motivate the course. I will say why this is an important course for you, for your careers, and so on. I will touch upon certain core architectures of generative AI. So this is just a very high-level overview. In the upcoming lectures, we'll obviously dive into the details, and we will go through all the concepts in a lot of rigorous detail. But we're not going to do that today. We are just going to go through the overview today. Okay. And I'm also going to touch upon some course logistics and policies. Even though I had actually planned to do an elaborate course logistics introduction today, I'm going to cut it short because there has been some recent changes in the course organization. So we decided to increase the number of seats because the course was in high demand. And therefore we got a new hall, and then we got more teaching assistants, which requires me to change some of the logistics that I had initially planned. So I will touch upon some course logistics today, but I will send more details on Brightspace, and I will also touch upon the logistics again on Thursday. Okay. This is because I just didn't have enough time to make all the changes after the course organization was changed. So apologies for that, but I will make sure that all the logistics informations are clear for you as you take the course. Okay. Right. So let's start the lecture today with a discussion. I'm sure all of you have used generative artificial intelligence, right? So I'm like, some of you may have dived into the concepts of generative artificial intelligence, but I'm pretty sure all of you would have used some tool of that generative AI comprises. So I would like to start by leaving the floor open. Is there like a particular tool or a particular technology or a particular use case that for which you used generative artificial intelligence and that just surprised you, that just blew your mind? So you all know that this is a very recent technology. So generative AI was not there, say, 5 years ago, but now it's just taking over the world. It's probably one of the hottest fields out there today, right? And I'm sure you would have all used different tools. You would have used foundation models, large language models, and even generative AI. So can someone tell me like an example of a situation or a use case that you found to be very helpful and that also really surprised you? Yeah. Can you repeat that? Sorry. Oh, okay. So recognition of the object recognition in text and video. Is that what you're talking about? Ah, right. Okay. Okay. Yeah, that's a good one. I first got surprised by the power of generative AI when I was using it for code. So I had like this really large code base, more than thousands of lines of code. And then there was this bug I was really struggling with for hours together. And then I used a generative AI tool, and it was able to figure out what the bug was in seconds. So that was one example where I really found this to be very powerful. Any other examples people have used yet? Uh-huh. Exactly. So going through the research paper, summarizing contents, giving you like the core details in a very digestible way, right? So that's an excellent use case of generative AI. Any other use cases? Yeah.
It adds the nature in the measurement that nature is quality. That's a very interesting.
Quality of what, sir?
LLM as a judge.
Judge, okay.
Yeah.
So the quality of judgments that
Yeah.
that was able to make. Mm-hmm.
These measurements technique with the other metrics.
Right. Oh, right. Very good. Yeah, that's a great example of generative AI in the real world. Yeah.
So in medical fields or in other fields, people use generative AI to diagnose patients' symptoms.
Exactly.
And also to generate assessments.
Mm-hmm.
No, diagnose and assessment books actually.
Okay, yeah, diagnose and assess patient records, and it's also quite good at it. The accuracy is very good, and it's also being used in production quite a bit in the medical area. Yeah, any other examples? Yeah, so we had code, we had medical research, we had like research papers, LLM as a judge. Yeah.
Example where LLMs are being trained or like to simulate real world transactions in a sense, like for example, I think Anthropic has this project like about an vending machine where like it's basically simulating a whole shop as an LLM.
Okay.
Like you're a shop.
Is that a financial application
like,
or?
Application operational financially, but I forgot exactly the name.
Okay.
Project vending machine, I think.
Okay. What exactly is the application?
So it simulates like how you would interact with the vending machine with like a shopkeeper, but like the LLM is the shopkeeper.
Okay.
So
okay.
Critically like trained to think as a human.
Right. So LLM as assistants, right? As human assistants, right? Yes.
About the generation and video generation, and sometimes you can tell it's AI stubborn.
Okay. Yeah. So AI has come a long way in image generation, video generation. Some of these applications are they have, like AI has made a large progress in some of these applications because there has been a lot of money poured into it. So the big tech companies like Google and Anthropic and Microsoft and so on, they're all interested in advertisements. They're all interested in certain types of applications, and they've poured a lot of money into AI development in those applications, and AI has become really strong in that. Code generation, image generation, video generation, all of these are applications where AI has become, generative AI has become really strong. And like you said, in some cases, you cannot even distinguish between an image created by Gen AI and an image created by a human. So it's that good now. Any other applications? Yeah.
Around the data that you can just convert it to something understandable for the machine. You can use the CRM system in a couple of minutes. Even a business music industry,
Right.
we just some process tasks, couple of generative AI, you have back to back, and you have a music industry. So
Yes.
I think the counterpart of all of these things is that you can handle huge amount of data
Exactly.
without any prior knowledge. And that's amazing, and it can be extended to any coding, even handling the whole company together.
Right.
It can be done. Yeah.
Yes. So that's a very important and interesting point. There is this aspect of scale that you touched upon. So just 5 or 6 years back, like AI was not capable of handling the scale of even some toy examples or toy environments. So we were talking about like at those even I would say 6 or 7 years back, the kind of examples we were talking about were like MNIST and other toy domains, which is nothing comparable to the scale of what AI can do today, and the kind of benchmarks AI is being used today. So yeah, scale. So generative AI has shown that it can really scale very easily and very efficiently to very large data sets.
The coding part, I feel if it's not like a very particular topic, in general, I think the Python code, R code, you ask how to analyze this, and ChatGPT or other generative AI tools can generate for us.
That's right.
But if it's like a particular topic, I don't have it.
Right. Yeah. Again, this goes back to the training data. So if there is like a niche, so maybe Python, it's still very good, but if there is like a niche language where there is a good chance that it's not trained at all on, then again, then that will be an application where it's not really strong. So like I said, generative AI the development has gone in a direction of where the money is flowing, and lots of money is coming in from a certain big tech companies. So it's like those applications where generative AI has really shown its promise, and in other areas it has got a lot of potential that is waiting to be tapped. So that's what I would say. Any other examples? Any other use cases that you liked? Okay, so we had like a very diverse set of examples and use cases that we saw, and that shows the power of the technology. So what we are talking about here is not something theoretical. It's not something academic. It's something extremely practical. It's something that's there in your life today. I'm sure you're using it every day. It's a part of your life, and it's making a huge impact on our economy, on healthcare, on education, and whatnot, right? So that's why we say this is actually a transformative technology, and we are living in transformative times because of this technology. So yeah, I mean, if this is a transformative technology that's impacting you in such big ways, shouldn't we understand that better? Shouldn't we know that better? Shouldn't we try to learn how these transformations are possible in a more deep sense, right? So, and that's what this course is all about. This course is all about trying to understand generative AI from a first principles perspective, and trying to see how it's able to achieve whatever it's able to achieve, and then also try to understand its limitations. Try to see like where it can be used, where it cannot be used, where it's doing well, where it's really struggling, and also get a glimpse. And I mean, like, I think in this course you will try to get a glimpse of the future. So we will when we look through the concepts, when we open the black box, when we dive deeper, we will understand this technology in a very deep level, and then we'll have a good intuition as to where this technology can be used and how this technology will evolve in the future, and how you can master it so that you can have really good careers in this field or in adjacent fields where you use this technology in those adjacent fields, right? So I don't think there is any field today that's not being impacted by generative AI. So it's a transformative technology. It's impacting every field out there. It's impacting it's impacting basic sciences. It's impacting medicine. It's impacting law. It's impacting education, finance, economy, whatnot, right? So let's try to understand more about this, and that's what this course is all about. Okay. Right. So the beauty of this technology is that within very few years, so generative AI was not really a force even 4 or 5 years ago, but within 4 to 5 years, we have seen a paradigm shift. So we've seen a paradigm shift in the capability of this technology within 4 or 5 years, or even less than that. So AI has gone from being able to analyze input data sets, and this data set could be images, it could be video, it could be text, it could be anything. And AI, even a decade ago, was only being used to analyze this input data and be able to predict or classify whatever data is being thrown at it, right? But today, AI has gone a step beyond that and is able to create new content, okay? And that's what generative AI is all about. But the fact that it's able to do this is something that's amazing. It's something that very few of us thought this could be possible so soon, right? So let's take an example. The slide shows an example. On the left, you have an image of a cat. So previously, when you didn't have generative AI, what you would do was show this cat to an ML model or an AI model, and the AI model, if it's a really good model, if it's really well trained, it will be able to say something like, it will be able to classify this image as a cat with a very high confidence, right? So this is all, even the best models 5 to 6 years ago was just able to classify the image with a very high confidence. So if you in 2019 or 2020, if I had a model, and if that model could, if I gave it this image, and if that model said this image is a cat with 98% confidence, then I would be really happy. I'd be really happy if the model could do that, right? But today, if I go to any large language model, Gemini, ChatGPT, Claude, I don't know what you use, and if let's say I give a prompt, which goes like something like this, right? Say, generate an image of a cat with an astronaut suit, So if I go to any large language model, any generative AI tool, and I give it this prompt, it can create the image that you see on the slide. So it can create an image of a cat in an astronaut suit. So if you think about it, this is amazing because it's extremely hard to get training data that shows cats in astronaut suits, right? I mean, this is something that's very unreasonable. It's very hard to get training data like that. I'm sure no AI tool would have been trained on pre-existing data sets that have cats in astronaut suits. But if you give a prompt now, within a few seconds, it's able to generate this image, right? And how is this possible? What conceptualizations, what algorithms, what breakthroughs have made such generations possible? I mean, this is something amazing, and we are going to just open the black box in this course. We are going to open the black box and see how these things are even possible, and how these things are possible in such an efficient way, in such a fast way, and also in such a in such a good way, right? And like the image that you see here, it's kind of clear. There are no ambiguities there. it's clear that, this is an image of a cat in an astronaut suit. And then for majority of prompts that you can think about, if you go to a large language model and if you give the prompt, it's able to do something reasonable. It's able to provide you an image that's a reasonable approximation of what you had in your mind, right? So that's a part of the technology, and that's why this technology is so amazing. So the key question is, I keep saying this, right? I keep saying that within the last 4 to 5 years, we've been able to achieve so much in generative AI. And then, like, if that's true, there are 2 key questions here. The first question is how? How was it possible for us to get to all of these amazing advances in such a short span of time, right? That's the first question that we have. And the second question is why now? Okay, I emphasize the second question because the core principles of neural networks and the mathematical equations that power some of the breakthroughs were actually invented in the 1980s. They were there even during 1980s or 1990s. But still, we are only seeing the breakthroughs now. The application breakthroughs, we are just seeing them now. So then why now, right? So in the literature, there is this term called convergence triangle. I don't know if you've heard of it, but it's very relevant for the course as well as for generative AI. So it's called the data model compute triangle or the convergence triangle. Okay, and in the convergence triangle, there are 3 key components that we recognize as being important, as being fundamental for the generative AI breakthrough. The first is the existence of massive data sets. So the data sets are the fuel that propel the technology, right? And that's the first component. That's the first component of this convergence triangle. The second component is specialized hardware, and I'm sure you've heard of this term before. The specialized hardware that we're interested in here are GPUs and TPUs and other compute that have made all the breakthroughs possible. And then there are architectural breakthroughs. Then there are algorithms and architectural breakthroughs. So that's why we have like 3 components, and we need progress in all the 3 components for us to make progress in this technology. So it's a common misconception that it's just the algorithmic breakthroughs that make the technology as good as it is, right? So that's a very common misconception. So there is a common misconception that if we can get better and better algorithms, that in itself will be able to make us progress faster in this field. But that's not true. We have to actually make progress in all the 3 aspects. We should be able to make progress in the dataset aspect. We should be able to make progress in the hardware aspect, as well as the algorithmic aspect for us to be able to make progress in this field, right? And with respect to the hardware, with respect to like GPUs and TPUs, there is like a special law. It's called the Moore's law. It's just an empirical law. It's not a physical law like you see in physics. There is this law called the Moore's law, which essentially states that the number of transistors in a computer chip essentially doubles every 2 years, right? So the Moore's law, it's like an exponential law, and it's something that has been studied for about 100 years, I think, and at least for the last 100 years, this law has been true. You can see an exponential curve, and every 2 years, the number of transistors in a chip is doubling. So your compute capacity is growing in an exponential fashion. And that's one of the key reasons why we are seeing some of the great breakthroughs today. And we didn't see them in 1980s and 1990s. And you may have even heard that during the late 90s, there was an AI winter, right? So from 90s to 2010 or early 2010, there was an AI winter. There was not much progress happening in AI. There was not much funding coming into AI. There were very few people working in AI during that time. And the reason is because the hardware aspect and the hardware aspect was not there, right? So that's why I keep emphasizing that we need to make progress in all the 3 aspects for us to make progress in the field. So this course will touch upon all the 3 aspects. This course will pay more attention to the algorithms and the architectural breakthroughs, but will also touch upon all the 3 aspects. So it will talk about data sets, it will talk about hardware. This course will also talk about the algorithms. of course. And with respect to data sets, it's about like acquiring data sets, acquiring good quality data sets, organizing those data sets, and then using them in a very efficient way for training. And that those comments also hold true for hardware. We need like really good high quality hardware, and then we have to be able to make efficient use of the hardware. So we should be able to parallelize computations and process the data sets in a more efficient manner. And that's what the hardware has to do. And then once we should do all this in parallel to improving our understanding of the algorithms and improving our improving the quality of algorithms that we are using for AI, right? So yeah, any questions on this? Okay. So then let's just see what generative AI is all about. So if you ask if you want a very layman definition for generative AI, it's simply a type of AI that's capable of creating new content. Okay. So new content could be text, it could be images, it could be audio, it could be video, it could be code, it could be anything. But if you have an AI model or an AI agent or an AI machine, anything that is capable of creating new content, then that is classified as generative AI. Okay. So in a first principles perspective, the AI model, when it aims to create new content, it first identifies pattern within massive data sets. So you know that all of these AI models are trained on massive data sets, right? So really, we are talking about petabytes of data. We're talking about really, really massive data sets. So these AI models are trained on petabytes of data. And the first thing it's trained to do is to identify patterns within these massive data sets and then use the pattern to generate original output. Okay. So if you think about humans creating anything, subconsciously, there is a lot of study on this in psychology, in cognitive science, and so on. And there have been some results that have shown that humans subconsciously learn patterns and then use those patterns to generate new information, right? And there are several fields in which this is very apparent. Like we can take some examples in mathematics. In mathematics, I'm sure all of you would have seen sequences, right? Arithmetic sequences, geometric sequences, many different types of sequences, harmonic sequences, and so on. So if I give you a sequence, let's say I give you a sequence 0, 3, 6, 9, 12, right? Let's say I give you the sequence. Now, if I ask you to give me the next element in the sequence, I'm sure you would say 15, right? So how are you able to generate the next element? How are you able to create like this new information that I didn't give you? So if you think about it, the human brain has subconsciously identified a pattern in that sequence. The pattern is that this is an arithmetic sequence with the difference being 3, right? And the human brain has subconsciously identified that sequence. And then now if you ask the human brain to provide more elements in that sequence, it's very easy for the human brain to do it. It's able to, it can give you like several elements in that sequence. So that's the intuition here, okay? So in the entire field of artificial intelligence is trying to mimic the human brain. So we are trying to mimic the human brain. We are trying to understand the human brain better in some sense. And we're also trying to use our understanding to create useful tools in another sense, right? So we are trying to see how, we are trying to understand our own brain in a better way. We are trying to see how humans do something. And then we are trying to mimic that in maybe even a crude way in computer science. And that's what the entire field of AI is all about. And in generative AI particularly, the intuition has been that the human brain is constantly receiving new information, is actually processing it's actually processing large amounts of data, and this large amount of data is being processed through time, through space, through variations in time, space, and so on. But it's able to process that data, learn patterns, and create new content, right? And that is what we are trying to mimic in generative AI. We are trying to mimic this phenomenon and we are trying to make these models make new content. We are trying to train these models to make new content. Okay. So fundamentally, generative AI has two things that it does. So there are two aspects that are core to how generative AI functions. One is training, where that's the first phase, where you just use vast amounts. When I say vast amounts, I'm talking about petabytes of data, like really large amounts of data. And usually this is human created content. And this is like, you can think of Wikipedia, think of like GitHub, think of Google, Google Books. So think of these, very large databases. So that's the data set or the database that's used to train AI. And this particular data set, when it's fed into an AI model, the AI model is trying to understand patterns, underlying patterns. And from a mathematical perspective, it's trying to understand the joint probability of the different elements in that data set. Okay. And it's trying to process all of that in the training stage. And after all the training is completed, when you want the AI to create something new, there is an element called prompting, right? So when you use a foundation model, when you use large language models, you open the large language model. It could be any large language model. It could be ChatGPT or Gemini or Claude. I don't know what's your favorite large language model is, but you open the model, and the first thing that you do is you enter a prompt, right? So you enter a prompt, and then the AI model, which is trained on large amounts of data, is expected to generate a response by predicting the next logical element, right? So if you we just saw one example of creating an image of a cat in an astronaut suit. So that's the prompt: create an image of a cat in an astronaut suit, and that's the prompt the AI model gets, and then it tries to predict the next element of that sequence, and that's the image that it has to generate. It generates that image and returns it to the user. So that's the internal working of any generative AI, a tool or model. Okay. So the functional opposite of generative AI is what we call as a discriminative AI. So there are several terms that are being used in the literature. So discriminative AI is also called predictive AI. So you will find predictive AI in the literature. You'll find discriminative AI. You'll also find terms like traditional AI. So the functional opposite of generative AI is either they all mean the same thing. Discriminative AI or predictive AI or traditional AI, they all mean the same thing. So discriminative AI works in a very different way. So the idea is to, for a discriminative AI model, the idea of that particular model is to analyze existing data to categorize or distinguish between different items. So the objective of a discriminative AI model is to actually figure out a decision boundary, right? So the discriminative AI model is given data sets similar to how a generative AI model is given data sets. Discriminative AI model is also given a data set. And the discriminative AI is actually trying to find a decision boundary to classify or cluster the data that's given to it, right? And the objective is not to create new content. It's not possible for discriminative AI to create new content. And for discriminative AI, the way it works is it also has a training phase. So every AI has to be trained. So discriminative AI also has to be trained. And during training, so there is like vast data sets that are used to identify specific features that most effectively differentiates the two or more groups, right? So you've seen binary classification, multi-level classification, right? So if you've taken any discriminative AI course, I don't know if you've taken a course on supervised learning or unsupervised learning or any other machine learning course, or if you've used it in your projects and so on, you would know that this particular tool is being trained to figure out or find specific features that most effectively differentiates a set of classes, right? So it's able to do binary classification or multi-class classification. And in this case, that from a mathematical perspective, from a first principles perspective, this is actually trying to find it's interested in the conditional probability, right? It's not interested in the joint probability, but the conditional probability. Okay. So the discriminative AI actually ignores the overall structure of the data and focuses only on the differences needed to make the decision. right? In the generative AI's perspective, the generative AI is actually trying to understand the pattern or the structure of the data. So it's trying to understand the structure of the data, it's trying to understand the pattern so that it can create new content. But discriminative AI is not trying to understand the content, it's just trying to figure out a decision boundary. Just figure out a decision boundary so that it can classify a cluster, right? So discriminative AI is also called predictive AI. It's mostly used for prediction. And when it's used for prediction, it's provided with new unseen data, and the model determines which side of the decision boundary this data falls on, and then assigns a label or a probability score to the data. So you would have heard terms like classification and regression and clustering and so on. So if you have a classification problem, you could use a discriminative AI tool. You could ask it to classify the data that's provided to you. There are several classification algorithms. I don't know, have you heard of SVMs? Yeah, good. So have you heard of decision trees, random forests, SVMs? They're all models that we classify under discriminative AI. Okay, and these are models that will take the data, whatever data you give it, it will just take the data, and it will first be trained, but after that, during deployment, it will determine which side of the decision boundary. It will determine a decision boundary, and then it will decide which side of the decision boundary a new data falls in, right? And you can use it for classification or regression or whatever application you're interested in. So this is what discriminative AI does. So let me be very clear, right in the first lecture, that this course is on generative AI. Okay, we are not going to talk about discriminative AI. We're not going to talk about anything. We will touch upon discriminative AI just to show the differences between a discriminative AI algorithm and a generative AI algorithm. But this course will focus purely on generative AI. There's going to be no serious discussions of discriminative AI. For discriminative, if you're interested in discriminative AI, there are several other courses in computer science, in systems design, and other in engineering and other fields in Carleton, which goes into the details of discriminative AI. So Comp 3105, I think that's Intro to Machine Learning. Comp 3106, that's Intro to AI. Comp 4107, I think that's Neural Networks, and so on. So there are like several other courses out there that does discriminative AI. If you're interested, you can take those courses, or maybe you've already taken those courses, but we will not go into the details of those algorithms, right? So this particular course, Comp 5801H 49008, only covers generative AI. And so when I say it only covers generative AI, what I mean is that I'm interested in algorithms, I'm interested in models that will focus on creating new data and not classifying existing or old data, right? So here I'm going to make a clear distinction. I'm going to show that there's going to be a clear shift between AI that classifies or predicts to AI that creates. Okay, so just to make that clear, right in the first lecture, there's going to be almost next to zero discussion about discriminative AI in this course. So just the last, say, 5 minutes, I'm talking about discriminative AI only to show the functional opposite of generative AI so that you can understand generative AI better, right? So generative AI, we will focus from a mathematical perspective. We will focus on probability and density estimation. So the probability estimation will be the what. So it will say what functionality you're trying to achieve, and the density estimation will form the how. It will say how this particular objective is going to be achieved. I'll go into more details in the rest of the lectures, but I'm just trying to make a distinction here between generative AI and discriminative AI, right? Right. So the course objectives for this particular course will be to learn the foundations of modern generative AI architectures. Okay. So I'm not going to talk about SVMs. I'm not going to talk about decision trees or random forests or some of those classification clustering algorithms. I'm going to talk about modern generative AI architectures. I will give you some examples in 1 or 2 slides. Once I talk about those architectures, remember the convergence triangle, right? Remember the convergence triangle. We are not going to restrict ourselves only to the algorithms. We are going to make a holistic effort. We're going to make a holistic approach We're going to talk about implementation skills, where we will talk about certain aspects of compute. We'll also talk about certain aspects of data, right? So these are all the practical aspects, components that we need to make these architectures functional, or to make these architectures practical in the real world. We will also do a very critical analysis of the state-of-the-art models in generative AI. Okay, we will analyze them in a very critical way. We will try to understand them. We'll open the black box, and then we will discuss the advantages and limitations of these methods. So understanding these architectures is understanding these generative AI architectures is the goal of this course. Okay. Okay, so why should you take the course right off the bat? So I touched upon these points, but I just want to emphasize them again because they're very important. So AI is transitioning from a niche research field to a general purpose technology. So I started working in AI, say, about 11 years ago. And at that time, I took a course in machine learning. I think, I took a physical in-person course in machine learning at the University of Waterloo. And then there were I think we were about 10 students sitting in the course. There was a large hall, it was almost empty. And I mean, machine learning at that time was being still thought of as a very niche research field, and there was just limited interest. But you see, within a decade, even this lecture hall is full. There are several machine learning courses happening at the same time at Carleton, and I was told that almost all of them are full, right? AI is just growing leaps and bounds, and it's becoming a general purpose technology that's impacting lives in a huge way. And learning the principles of this particular revolution is going to be very helpful for you. It's going to be very helpful for your careers. It's going to be very helpful for you when you go into the job market. I know some of you may want to go into the job market and work for other companies. Some of you may want to start your own companies. Some of you may want to go into grad school and go into research. Generative AI will help you in all of these aspects. So generative AI is it's getting a lot of interest from venture capitalists if you're interested in entrepreneurship. So we will discuss some ideas in this lecture, in this course. And if you are very, very interested in entrepreneurship, you have a lot to gain from learning the principles of generative AI, right? If you are interested in research, generative AI is one of the most hottest topics in research today. If you want to do a PhD, if you want to do a master's in generative AI, understanding the principles from this course will really help you. And even if you want to do a master's or PhD in other fields, let's say you want to work in, I don't know, in databases. Let's say you want to work in software engineering. Generative AI is making a very significant impact in all of those fields. In software engineering, Copilot, you see the revolution that Copilot has brought in software engineering. So even if you're interested in other fields, learning generative AI is going to give you a significant advantage in research and grad school aspects. This is a $1 trillion opportunity. That's the word from economists. Economists say that this is McKinsey and Company has an article which estimates that generative AI could add $2.6 trillion to $4.4 trillion annually to the global economy across 63 use cases. So McKinsey and Company has just surveyed 63 use cases, and then just for those 63 use cases, it's estimating that there would be about trillions of dollars added to the economy in just those use cases that McKinsey and Company has considered. So there's a paradigm shift in the industry today. So the industry is now transitioning from building small task-specific models, which is what we call discriminative AI, to deploying and fine-tuning foundation models, which is generative AI. So there is this paradigm shift, and understanding the principles of this paradigm shift will clearly give you an advantage. Okay, so we are seeing an explosion of the convergence triangle, and that is something that you will explore more in this course. And even if you're not really interested in AI at all, generative AI, learning certain aspects of generative AI is helpful for you because it gives you a productivity leap, right? So I don't know, you may want to become artists, or you may want to become You could become like historians. I mean, you could become sportsmen. I mean, there's like anything that you want to become. You can actually go into any area. But learning generative AI will give you productivity leap in that area, in that field. So that's why learning this now is useful, and taking this course now is going to be very helpful for you. Right. So let's dive a little more deeper. Let's understand what generative AI is all about. So there are four pillars, what we call four pillars of this revolution that you're seeing today. So this is just from an architectural perspective. So remember the convergence triangle. One of the aspects of the convergence triangle is just the architecture, right? The architecture, all the algorithms. There are four algorithms that have been central to the generative AI revolution. So those are generative adversarial networks, GANs, variational autoencoders, VAEs, transformers, and diffusion models. So these are like the four core architectures that are powering the revolution today. So these four architectures represent the foundational breakthroughs of the last decade. Okay, and the state-of-the-art models. I don't know, like you may have used Midjourney or Stable Diffusion, or even large language models, right? Like ChatGPT or Gemini. The state-of-the-art models actually just use a fusion of these four different algorithms, right? So most of the algorithms that are state-of-the-art today, they are either one of these four architectures. They are using either one of these four architectures, or they're using a combination of these four architectures. Okay, so if you learn these four architectures really well, then you have a good grasp of the cutting edge of generative AI today. Okay, and this course will dive really deep into these four architectures and just open the black box and make those make the mathematical aspects, the algorithmic aspects, as well as the architectural aspects of these four models very clear. Okay. So when you're trying to understand these four models, the good place to start would be to start with recurrent neural networks. Okay. So if you've taken a course on neural networks, you've definitely seen recurrent neural networks, but we will start this course again with recurrent neural networks because the first particular pillar of generative AI is probably transformers, and transformers were first initially proposed as an improvement to recurrent neural networks. Okay. So if you think of neural networks, if you've taken course on neural networks, or if you've had any neural networks, the first building block of the first, probably the most fundamental neural network that we've learned is a feed-forward neural network, right? A feed-forward neural network is the simplest neural network that you can think of, and we call those as static neural networks. And these static neural networks are problematic because they can only take a particular snapshot of a data at a particular point of time, and then train using the data or classify or do something with that data. They cannot actually think about sequence, or they cannot think about they cannot keep context in mind. And therefore, this particular feed-forward neural network is not really helpful for sequential data. So when I talk about sequential data, I'm thinking about text, speech, or time series data. So feed-forward neural network is not really effective in all of these use cases, except if you provide all of the text, all of your speech that you have in one shot to a feed-forward network. Okay. So unless you do that, unless you just use everything in one shot, which is very hard, especially if you have a large sequence, your feed-forward neural network is not helpful for sequential data. Okay, and that's when researchers introduced recurrent neural networks, and the architecture is just shown in this slide, where there is like a recurrent neural network on the left-hand side in a rolled fashion, and then that's just unrolled on the right-hand side, where you have loops, and within the loops you have a certain hidden state representation, which is the state A that's represented. This particular hidden state is it's a latent vector that persists across all the different data that a recurrent neural network sees. Okay, and this particular latent vector is it's maintained across the sequence, and it kind of summarizes all the past information. Okay, and whenever there's some new information that's coming in, the new information is synthesized with the past information, and that is used to predict or classify. right? And that particular paradigm is what recurrent neural networks introduced. Okay, so recurrent neural networks were a revolution for sequential data. That it really made a big difference for sequential data like text, speech, or time series, and it was very effective, but still it had some critical limitations. Okay, so the major limitation was the problem of vanishing gradients. If you've taken a course on neural networks, you would have learned more about this, but we will also discuss more about these disadvantages of RNNs, problems of vanishing gradients, information bottleneck, and sequential computation. So when you talk about vanishing gradients, to give you an intuition of vanishing gradients, think about a really long sequence. Okay, so in this particular sequence, you have only 4 elements. You have only 4 elements that is shown here, but then there is like this particular dot that I'm using to represent a very long sequence. And in a long sequence, whenever there is new information, once this new information is synthesized, the loss function is usually updated using backpropagation, right? So when you're doing backpropagation, and if you're doing a backpropagation across a long sequence, usually what happens is that the error is multiplied by a small fraction at every time step. And then when it comes to the end of the sequence, the error is almost gone, right? It's almost vanished. So therefore, when it comes to the end of the sequence, there is really no gradient to update your weights, and the model effectively does not update after a particular time step. Okay, so that's the problem of vanishing gradients, and that has really restricted the applications of recurrent neural networks. The second problem is information bottleneck. So if you're trying to use a recurrent neural network in a really long sentence, okay, think about like think about trying to recognize spoken language where you have a very, very long sentence, and then you're trying to use a recurrent neural network to process that long sentence. Then you will usually find the recurrent neural network struggle because there's an information bottleneck. So it cannot process information up after a particular limit. And then the other problem is sequential computation. So recurrent neural networks has to process each word. So if you want RNNs to process a sentence, RNN will process each word one at a time, right? So the problem with this is that you cannot parallelize your compute across a large data set or a large text or a sentence that you've got. So you have to process them one at a time, and the particular algorithm that you're using is usually linear in the input space. So it's order of n or sometimes even quadratic. So because you cannot parallelize the algorithms, the algorithm is slow and it's not very effective in large data sets. Right? So RNNs were a breakthrough, but then they had like some critical limitations that prevented its wide application. So after RNNs, to address these limitations of RNNs, we had another breakthrough called the attention mechanism. Okay, and the attention revolution recognized the bottleneck of RNNs, that there is this loss of detail over long distances. So it tried to address that, and then we had a new architecture called as the attention mechanism that allows for parallelization of the model across data. So the attention mechanism, the attention model was different from RNNs, was a fundamental advancement over RNNs because they were able to parallelize information and also learn in a more efficient manner. So I don't know, you may have heard of this particular paper, Attention is All You Need, right? So it was a fundamental breakthrough in AI. The attention mechanism does something different. It actually looks at an entire sentence at the same time, right? So let's say you have, let's take a simple sentence. Let's say I ask you, what is your name? Okay, so let's say I ask you this question. And if you're using an RNN to process that sentence, the RNN will go one word at a time. So it will go, what is your name? So it will go just one word at a time. But then the attention mechanism will look at the entire sentence as one block. Okay. And then it will look at this entire sentence and then see which words in the sentence are most important to the current word that the mechanism is trying to focus on. Okay, so attention mechanism brought some new ideas like global context, it made it clear that, like, unlike recurrent neural networks, the distance between words no longer matters. So it does not matter like which word came after which word. So when you're saying a sentence, it does not matter like what is the order of the word. So attention can just see the global context. So a good example will be like think of a sentence that I give you where I jumble the different words, right? And if you're strong in the language, you can just rejumble the words quickly because you understand, the human brain understands context. Okay. Yeah.
Isn't the positional encoding for that?
Yeah, so positional encoding by default is turned off in attention mechanisms. You have to, it's like an additional input that you have to give to an attention mechanism if you need to use it. But by default, attentions don't have any positional encoders, any positional encoding. Yeah, so the distance between words no longer matter. You're looking at the sentence as a whole, and then you're trying to process the sentence as a whole in the attention mechanism. So the attention mechanism led to another architecture called transformers. Transformer architecture uses the attention mechanism, and that was the single architectural breakthrough that made large language models like GPT possible. Right? You may know that the full form of GPT is generative pre-trained transformers. So GPT is just a transformer under the hood, and attention mechanism makes transformers possible, and transformers makes large language models possible. Okay, so the attention revolution was a key step, and that was one of the pillars that I talked about. So when we talk about generative AI today, we talk about 4 pillars. Just to remind you, we talk about GANs, generative adversarial networks. We talk about variation autoencoders. We talk about attention and transformers, and we talk about diffusion models. Right, and one of those pillars is attention, and this is the breakthrough that I talked about. So this is one pillar. Right. So this is an attention heat map gives you like it just opens the black box. It gives you information under the hood. So let's consider a sentence. So this image shows a sentence. The cat chased the mouse. Okay, so that's the sentence. So the attention mechanism creates this heat map where the cells which are dark shows low attention, low relevance between 2 words, and the cells which are bright shows high relevance. Okay, so if you take the word if you take the word cat here, so if you take the word cat on the can you see my arrow? Yeah. So if you take the word cat here, you see that the mechanism is providing more weight or more importance to the word chased. Okay, so this is like the subject verb relevance. Like if you're a linguist, you would like if you're a linguist or even as a layman, if you look at a sentence, you would probably give importance to the subject, the verb, the adverb, and so on. So those are the most important aspects of a sentence. And you can see that the attention mechanism more or less captures that. So if you take the subject, it's giving importance to the verb, and then if you take another example here, there is like this fast. There's this verb called fast, the adverb fast, and then there is the verb chased. So then it shows that when you have the verb and the adverb, the particular relevance is high. So it shows that there is more attention that you have to give to the verb adverb relation, right? So usually if you make a heat map of the language that you're trying to train, you will get a particular pattern similar to what you see in this image. More or less, you will get the same pattern. The attention mechanism is able to process the sentence in such a way that it can give more importance to the verb, to the noun, to the adverb, and so on, and their relations, and it's able to capture that well. And that's the power of the mechanism. That's the power of the model, and that's why it's so effective. Okay? And the other advantage is that attention mechanism can compute information, can process data in a parallel manner, right? So because it can do things parallelly, you can now deploy this mechanism in parallel across a large data set. This is unlike recurrent neural networks, which has to process data in a sequential manner. Okay. All right. So let's take a discussion point. So transformers treat all words as having an equal distance from each other. Okay, unless you switch on positional encoding, transformers will actually treat words to have the same distance from each other. In doing so, have we lost the flow of time that RNNs captured? Right. So recurrent neural networks were really good at capturing time, but transformers don't capture time. So is position just a feature we add back in, or is it fundamental to how intelligence perceives the world? Right. So this is a philosophical argument that's going around, and so the question is position just a feature, or is it fundamental to how intelligence perceives? Is it fundamental to how you, as intelligent beings, perceive the world? So it's not very clear. There's a lot of research happening on this in the fields of cognitive science and psychology and so on, where people are trying to understand what intelligence really focuses on, right? And how intelligence kind of classifies different things. If we have good answers to these particular questions, it will help us create better algorithms. It will help us create better models. Because essentially what we are trying to do is we are trying to mimic the human brain. Right? We're trying to mimic the human brain. We're trying to borrow ideas from how the human brain is doing things, and trying to create a miniature version of that in these computing algorithms. Right? So think more about it, and also read more about it. There is a lot of literature on this, and transformers show that even though we have lost the flow of time that RNNs captured, our methods have become more efficient. So at least from a transformer perspective, it's been a win. And transformer is able to process an entire document, and it's also able to create new knowledge, right? So transformers is actually a generative AI algorithm, but RNNs is not generative AI. RNN is still a discriminative AI algorithm because RNN is not able to create new knowledge. Okay. But even though RNN really focuses on the flow of time, it's not able to understand context and information and use that to create new knowledge. But the transformers can do it. So that's the power of the transformer here. Right. So once we learn about transformers, so we'll start with recurrent neural networks, and then we will talk about transformers, and then we will talk about two particular architectures, transformer architectures, which are very popular today. Right. The first architecture is GPT, generative pre-trained transformers, and the second architecture is BERT, bidirectional encoder representation from transformers. So these are two transformer architectures which are very popular today, and we will look at both of these architectures in detail in the course. So GPT is actually just is what we call a decoder-only architecture. The objective in GPT is to have an autoregressive loss, where the objective is to learn a causal language modeling. It is to do a causal language modeling. The objective is to predict the next token based on the preceding ones, right? So GPT here is a generative AI tool, and the strength of GPT is to create new knowledge, to do like creative writing, coding, open-ended conversations. So you can think of GPT as a storyteller. Can create new knowledge, create new stories, and then provide that information to you. On the other hand, BERT is an encoder-only architecture, where the idea of BERT is to do masked language modeling, where you actually consider an entire sentence, and then you mask certain words in that sentence. So let's take an example: the cat chased the mouse, right? Like the same example we had before. And if you take that sentence and then mask certain words in that sentence, that will be the data set that is used to train BERT. Okay, so you mask certain words and then see what BERT predicts, and then you use the word behind the mask as the ground truth. Okay, so then you can make a loss function between this ground truth word and the masked prediction of BERT, and then use that to train BERT. Okay. So BERT is used for sentiment analysis, question answering, and named entity recognition. You can think of BERT as a linguist, right? It's a linguist which is able to do like sentiment analysis and so on. So we will look at these two architectures in super detail, GPT and BERT, right? So another question for thought. So GPT was trained simply to predict the next word. is prediction the same thing as understanding? So there is a raging debate on this. I don't know how many of you are active in Twitter. So if you're following Elon Musk and I don't know, Jan LeCun and all the top researchers or entrepreneurs in Twitter, now it's called X, sorry. There is this raging debate about is prediction the same thing as understanding? Okay, so some people believe that understanding is just really sophisticated prediction. So if you understand something very well, you can just predict really well as well. So then some people believe that understanding is just sophisticated prediction. So if you can predict the next word perfectly every time, do you actually eventually develop a world model? So do you actually understand things? You develop the world model, or are you just a stochastic parrot, right? So there are two sides here, okay? And if you're following the debates on X, then you will see that there are researchers who clearly belong to one side and the other set of researchers who clearly belong to the other side, where people say that if you have a parrot, you can train the parrot, but the parrot is not really understanding anything. It's just repeating what you're saying.
Do you have a side on that?
So yeah, so my side is that I don't think prediction is the same as understanding. Okay, so that's my side. But if you belong to the other side, there's really no offense. So there is really good arguments for both sides. But it's for now it's like it's a subjective it's a subjective thing. Depends on like which side you belong to. Right? So in this context, there is like a really good experiment that was just done very recently. It's called the Othello GPT experiment. Okay, so I have the link of that particular paper on the slide. Read more about it if you get a chance. So in this Othello GPT, I'll just tell you a summary of this experiment, right? Like if you're like me, if you think that prediction is, if you think that prediction is not simply sophisticated understanding is different from prediction, and you need like different mechanisms for both. Then Othello GPT experiment is trying to convince you to go to the other side. Okay, so in the Othello GPT experiment, what the authors do is to consider a game called Othello. Okay, and then not provide the rules of the game, just provide. So Othello is like a board game, and then you have pieces of elements on the board similar to chess, but the rules are very different. It's not like chess, but it's like a board game like chess, and you have like coins on the board. And in this experiment, the authors show that just by looking at the pieces of the board, a particular AI model is able to understand how Othello is played. Okay, so the authors show that you can go from prediction to understanding. Okay, but again, there are several limitations to that experiment. There are problems like over parameterization. The game itself is like it's just like a toy domain and so on. But this experiment is trying to convince you if you're like me, if you belong to the side which says that understanding is not prediction, they are different. Othello GPT experiment is trying to convince you to go to the other side. Just read about it. It's interesting. Yeah. Any questions so far? Yeah.
I was thinking that maybe the difference between prediction and understanding would be related to the context that we want to predict. I mean that, for example, mathematics, we want to predict something. Next step based on some pattern. It should be same because we should understand the pattern and then predict based on this pattern. But for example, in the text, we can predict as humans without we can predict without understanding the relation between different words in a sentence and without understanding the coherence of the sentence or text.
Right. So the particular relevance here, the relevance of the question here, the philosophical relevance of the question here is to do with the training mechanism, right? So like if you're learning for an exam, there are two approaches that you can take, right? If you have like several textbooks for the course, you can just go ahead and just memorize all the answers for the exam, right? And then you can take the exam. So that's like just pattern matching. And that's you're building a predictor. You're pattern matching, building a predictor, and using that in the exam. Right? And the other approach is to understand the material from a first principles perspective, and then use that understanding again to answer questions in the exam. Right? So there are these two things that you can do. So the prediction is understanding side says that they are essentially the same thing. It's trying to say that it's the same thing. It's just like different ways of doing it. So like if you think about it, if someone can really memorize very well, and they would also get like really good marks. And if someone can, on the other hand, if someone can really understand something in a very fundamental way, they will also get the same marks. So I mean, in that sense, it's the same. But from a functional, from a usefulness, from utility perspective, understanding is a lot better than pattern matching, because understanding lets you know something from a first principles perspective, and it is like something that's so fundamental that can help you create new knowledge, like create fundamentally new knowledge. So if you think of like some of the biggest breakthroughs of the 19th century, like I don't know, some maybe the most fundamental theorems of the 19th century was the uncertainty principle or the relativity principle and so on. Large language models really cannot, even though they can generate new information, they cannot make some fundamental breakthroughs in that way yet. And that's because they don't really have understanding. So I mean, that's my philosophical positioning. But there are people who believe that if you can really keep doing prediction very well, then you will develop those skills. Right? Yeah. So there is like a lot of interesting interesting literature on this for you to read. Othello GPT experiment is like a recent literature that I can refer you to, but there's a lot of content out there for you to read on this. Okay, so once we go through like transformers and GPT and BERT, we will talk about a very important principle for large language models called RLHF, reinforcement learning from human feedback. Okay, so currently there is a course on reinforcement learning that Professor Junfeng Wen is teaching. I think it's Comp 5016 or something. So if you want a really deep understanding of reinforcement learning, I would refer you to that course. We are not going to go deep into reinforcement learning. But we are just going to touch upon reinforcement learning to understand RLHF. Okay, so this particular principle is introduced because we have a problem called the base model problem. So the base model problem is the problem that the model is, let's say you have a model that's trained on the internet. Okay, so this particular model can generate toxic content or follow instructions poorly. So the internet is a place where you have all kinds of data, right? So you have hate speech in the internet, you have biased information in the internet, you also have like really good literature on the internet. You have everything in the internet. So if you just sample data at random and then train a model, you don't know if you're building a scientist or I don't know, or a con man, or you really don't know what you're doing because you're just doing all of these things at random. So the final output that you get out of these models could simply hallucinate facts. It could generate toxic content or follow instructions poorly, right? So now the principle of RLHF is trying to correct that particular problem. It's trying to use human insights, human inputs to rank model outputs from the best to worst. Okay, so humans will look at different models, different outputs that a large language model can generate, and then it will rank it from the best to the worst. And then we are trying to reinforce the good outputs and then not reinforce the bad outputs. Okay, so that's why it's reinforcement learning from human feedback. So the reward. So in reinforcement learning, there is this idea of reward, and there is a reward function that the human is providing you. Here, the reward function is trying to train a second critic. It's trying to train a critic to learn human preferences and teach LLMs. So you want LLMs to mimic humans or be aligned with human values. So that's the objective here. So the outcome, the objective here is to have alignment, and therefore we are using RLHF to build safety guardrails to enable instruction following and have like distinct assistant phenomena, a persona that we see in ChatGPT or Gemini. So if you use ChatGPT or Gemini, you will feel that if you're using them really, if you really regularly, I mean, if you're using them multiple times a day, you will find that they have a distinct persona. Okay, so for the same set of, like, if you're using ChatGPT to help you for cooking, people have reported that ChatGPT kind of helps you cook. If you use ChatGPT's instructions for cooking, people have reported that the dishes are really bland. ChatGPT doesn't really encourage you to add too many spices. Okay. On the other hand, Gemini encourages you to add more spices. So I mean, there is this distinct phenomena, distinct persona that you find in these large language models, and that persona is coming from RLHF. Okay, it's coming from reinforcement learning from human feedback. We will look at the principles behind RLHF in this course. So the other pillar is variational autoencoders. So we talked about transformers. That's the first pillar. The second pillar is variational autoencoders. We'll also look at variational autoencoder in more detail. So the idea behind variational autoencoders is to compress high dimensional inputs, so high dimensional input like images, into a low dimensional latent vector. Okay, so here you have an example in the slide of an MNIST image that's being compressed from a high dimensional MNIST image to a low dimensional latent space. Okay? So this latent space now organizes data by features. The latent space is like a new space, which is low dimensional. It has continuous and smooth data. And then once you get the latent space, the advantage of variational autoencoders is that you can throw away all the original data. So let's say you have lots of original data, petabytes of original data. Now you have variational autoencoders can efficiently compress that into a low dimensional latent space. And now you can just throw away all the original data and then pick a random point in the latent space and then create a realistic new image from that point. Okay? So that's how variational autoencoders work. They are different from transformers. The principles are different. Variational autoencoders have certain advantages that transformers don't have. Again, similarly, transformers have certain advantages that variational autoencoders don't have. So when to use variation autoencoders, when to use transformers, I mean, these are the questions that we'll try to answer in the course. Okay. The third pillar is generative adversarial networks. Okay, so we talked about 4 pillars, remember: transformers, variational autoencoders, generative adversarial networks, and diffusion models. So the third one is generative adversarial networks. So this is like another generative AI algorithm that uses a principle called adversarial training for generation. Okay, so the principle behind GANs or generative adversarial networks is that you have two agents or 2 players, the generator and the discriminator. Okay, so you have a generator and you have a discriminator, and the generator is trying to create new data. So you just start from scratch. You define a generator and you ask it to just create a new data that looks like the data that you get from the training set. Okay, and the goal of the generator is to maximize the discriminator's error rate. Okay, so this is adversarial training, which means it's a zero-sum game. The generator is trying to outdo the discriminator, and the discriminator is trying to outdo the generator. So the discriminator here is trying to distinguish between real data and fake data. So fake data is the data that the generator creates, and real data is the data that's there on the data set. Okay, the discriminator is trying to discriminate these 2 data sets and is trying to minimize its own error rate. Generator is trying to maximize the error rate of the discriminator. So this happens in parallel. This happens at the same time. And that's why this is called adversarial training, where you have 2 networks that are improving at the same time. So this is a very different principle of generative AI. So this is a very different perspective of generating something. Okay, so transformers was one perspective, VAEs, variational autoencoders, is a different perspective, GANs is a totally different perspective. So GANs are really good at producing sharp, high-resolution images. Okay, so the output quality of GANs have shown to be very, very good, but they have a problem that training GANs is not very easy. Training GANs is really hard. You need lots of compute, and you have to be really careful with training, or you don't get good results. So you have to keep training until you reach a convergence point where the generator is so good that the discriminator can only guess with 50% accuracy. Okay, so after all the training, you're just going to throw away the discriminator and only use a generator because your goal is to generate new content, right? So then you wait until the generator does so well that the discriminator can only guess with 50% accuracy, which means that it's just no better than a coin flip. Okay, so you wait until that point. And once you do that, you throw away the discriminator and use a generator to generate new content. Okay, so that's the third pillar. Now the fourth pillar is diffusion models. Okay, so diffusion models are a very different perspective again, a very different principle of generative AI. The idea is to generate order from chaos. So the diffusion model uses a diffusion process where you have a forward step and a reverse step. Okay, and in the forward step, you just take an image. It's a very simple mechanism. You take any real image and then keep gradually adding Gaussian noise until the image is unrecognizable. Okay, so you take an image, maybe take an image of a cat, and then just keep on adding noise into it. At every step, you add a certain amount of Gaussian noise, and it leads to a stage where you only have like grains, right? Now this image is unrecognizable. Now, once you do that, after you do that, you can do the reverse step, which is creation, where the model learns to predict and subtract the noise step by step to recover the original image. Okay, so this is the process of diffusion models. And when it tries to do the reverse step, it tries to learn how to create an image from noise. So now this particular model is well trained to create new images just from noise. So now you can just give it some random noise and it will create new data. It will create like new knowledge. So that's the intuition behind diffusion models. So diffusion models are much easier to train than GANs. Okay, so their training there's like it's called stable training, where you don't have to really do anything. You don't have to you don't have to really engineer the training. The training is very simple, and it's also the current state of the art. Like if you've used Stable Diffusion, Midjourney, all of these image generation softwares, they're actually using a notion of diffusion model as their architecture. And the advantage is that you can do iterative refinement. You have time to fix errors and add intricate details, which other methods cannot do. Again, there are advantages and disadvantages for all of these methods, but these are the four architectures that are the state of the art, and that's being used across all of the generative AI tools that you're using today. Right. So once we go through all of those four pillars, we will talk about the responsibility gap. So we'll talk a little bit about ethics, bias, and governance, where we'll talk about the amplification of bias. So that's a real problem today in generative AI. So if a training set contains historical, gender, or racial biases, the model doesn't just learn them, it concentrates them. Okay, it amplifies biases. We'll see why, from a technical perspective, we'll see why this is happening. But the fact is that it is happening. Okay. So like an example is that if you ask the generative AI tool to generate a doctor, more or less you can be certain that it's going to generate a male doctor. Okay, and if you ask any generative AI tool to generate a nurse, you can be certain that the tool is going to generate a female nurse, unless you say that. Unless you say anything, if you just ask it to generate a nurse, an image of a nurse, or generate an image of a doctor, you will see that it's generating only male doctors and only female nurses. So this is bias in the data set that's being amplified by the tool. Okay? So that's one problem. It's very important. It's one of the reasons why generative AI is not used as much as we could use generative AI. So there are like places where generative AI can really make a huge impact, but they're not being used because of some of these problems. One of the problems is the amplification of bias. So that's one. The other is a problem of hallucination and not revealing the truth. Generative models prioritize plausibility over truth. Okay, so all of these large language models, the objective is for them to help you as much as possible, and not really tell you the truth. And this is probably because this is one symptom of reinforcement learning from human feedback. So when you're doing RLHF, you're trying to align these models to what you want it to say, You're not asking them to say what's the truth or what is factually correct. You're just aligning them to what you wanted to say. And therefore, you end up with the problems of hallucination and truth. Okay. Intellectual property and consent is another problem where you don't know who owns the output and was the training data legally used or not. Okay. So there is another discussion question here. I don't have time to go over it. If a model is trained on the entire internet, it reflects the internet's majority views. If we fix this by manually weighing minority data or forcing diverse outputs, are we making the model more accurate or less accurate to reality? Should AI represent the world as it is or the world as we want it to be? So that's the question that we have to think about. Right. If we have more time, I will talk about some additional topics like multimodal models, RAGs, continual learning, and so on. The ultimate goal here is for us to understand intelligence. So as you leave today, I'm out of time, so I'm just going to end here. This is the last slide. As you leave today, remember the objective of this exercise, the objective of going through this course is not just to learn how to code models. Okay, we are participating in the greatest intellectual experiment in history. Every time you tweak a weight or you design a new architecture, you're asking the universe, what is a thought and what does it mean to know something? You're asking some really fundamental questions, some of the most fundamental questions that have ever been asked. The ultimate goal isn't to get a better GPU or a larger data set. It's to answer what makes intelligence possible. Okay, so we are trying to understand ourselves as well as possible, and we are trying to build models that can mimic us. So I think that it was Richard Feynman who said, I cannot understand something that I cannot create. I cannot understand something that I cannot create. So we are trying to understand ourselves better by creating artificial intelligence. So yeah, so let me stop there, and I will see you on Thursday.